We discussed the aspects like classifications and all, some of the algorithms. Now, specifically, just what I am doing here is that because now we are talking about the concept of the regression actually. Now, the idea is just let me float some kind of the aspects here, regression, and as well as classification. Okay, of course, classification we have seen some sort of KNN, and then we have seen support vector machine, and then we observed some naive Bayes, uh, and then we have seen some sort of decision trees, and then random forest. Okay, similar to this, in regression, we are having some sort of algorithms, so which is linear regression, polynomial, and then we are having some support vector regression, and thereafter, even decision tree also can be used as a regression guide. Okay, and random forest can be used as a regression, and XGBoost kind of the regression, and naive Bayes also you can make use as a regression, and even KNN also. But don't get surprised because the flexibility here is the algorithms are not stick to the specific kind of approach, guys. Okay, have I started recording? Yeah, yeah. Okay. So they are not specific to the corresponding approach, and either of these algorithms can be used. I mean, these algorithms either can be used for the classification or regression task. Okay. So in the discussion of after completion of clarification about classification and regression, then we'll move to the other direction, guys. Okay. So and to specifically mention, let me recap. ML basically available in two formats: supervised, okay, and unsupervised. And in supervised, again, we are having two things now. Like now we have completed this classification discussion, and then we'll be having the regression, classification, and as well as the regression. Now, unsupervised, just not yet started, guys. Actually, just after completion of the regression, we'll go to the clustering aspect. The most commonly used unsupervised kind of thing. Apart from that, we're having some other principal component analysis, association rule mining, all those things follows. Whenever we are going and discussing about this kind of the aspects, definitely we'll talk about those considerations also. Now, in case of again clustering, we'll be having this DB scan and then k-means clustering, a hierarchy. Okay, hierarchy clustering. Now, in the certification also, what they are focusing is, of course, apart from the algorithmic perspective and what is the stat model behind it, even all those things we have covered in the earlier things, they remain same. And apart from those kind of the conventions, as this is the session where we are trying to understand the concept of the regression initially, and then we'll move to the appropriate metrics of the regression. Because we are getting 4 to 5 questions of the measures in terms of regression and as well as the clustering aspects. So it is always better before having the implementations, which are all the metrics or which are all the measures, so as to maintain as a part of this particular regression and as well as the classification. So that is what I named this particular topic as measures of regression, and then we'll talk about the measures of classification. Damn sure questions we are getting, guys, here. Uh, these questions, of course, pretty, if you are knowing about the metrics and how they work, then you can easily answer. Okay. Now, as a part of this thing, let me start with the regression aspect. Okay. So, regression, friends, in the classification, we know that S or no kind of thing, but in regression, it is not like that. It is giving some value, the continuous value. It is basically gives that how to identify the regression is tells the relationship. Okay, so just it is going to tell the relationship between the corresponding variables, and thereafter, the most important point is quantifies. Okay, quantifies the relationships. Okay, so quantify the relationship by using the set of equations. I'll reveal that what exactly the equation and how it is performing. And you know that guys, independent and dependent variables in the terminology of the machine learning. So it also determine okay how an independent okay how an independent variable just it is predicts the or use it to predict the value of the dependent variable. Okay, guys, see these machine learning, the beauty and advantage of this machine learning aspect is if once you are learning, then obviously you can make use of these things anywhere. Okay, so determine how independent variable predicts the value of the dependent variable. These things can be observed as the basis of the regression. So tells the relationship between the variables, quantifies the relationship by the set of the equations, and determine how an independent variable predicts the value of the dependent variable. Apart from that kind of the convention, uh, if I'm talking about the first category, actually simple linear regression. The aspect is clear, guys. Like consider, so simply it is considering only one independent variable. Okay, just it is considering only one independent variable or feature. Sometimes we can name that as a feature also. Some practitioners call that as a feature and one dependent variable. Okay, one dependent feature or variable. And whereas in case of the multilinear regression, one simple change. Okay, so consider many independent, okay, many independent features and one dependent feature. Observe here, guys. Okay, many independent features and one dependent feature. Now, to give the example, suppose if I'm taking this example like height and weight of the person. Okay, so here we need to create a model. I want to establish a kind of the model in such a way that if I'm giving my input as height, okay, then I can able to predict okay my weight of the corresponding person because generally what the model does is model just it is taking some form of the inputs and it is going to perform some activity and it is going to give the outcome. Okay, now similarly another example, okay, just with the examples we can see, and I want to purchase a house with a number of rooms, and based on the rooms definitely there is a price. And here the number of rooms is nothing but the independent feature or independent variable, and price is your dependent variable. Okay, and most commonly used example in our industry and all the things like years of experience and salary. Okay, because while fixing the pay and all those kind of things. Just we need to see the appropriate slot actually. Okay. Now observe here, guys. Most important stepping stone to understand the regression, and probably this is the best. The best way of understanding the regression. Okay. Now here, just if you are making use of as we have seen earlier, this regression is a kind of establishing a relationship between two, one independent variable and one dependent variable, maybe multiple also. For example, if I am taking years of experience here and the corresponding outcome salary here. Okay. Now, corresponding to this experience, maybe 0, 2, 4, 6, like that I'm taking. Maybe in between some are there, but for the example purpose, and there are some kind of the prices or salaries related to the corresponding salary. And 2 years experience some value, 4 years some value, 6 years some value, and maybe 8 years some other value. So what we're doing here, guys, just if you are integrating these two aspects, okay, if you observe this point, and there even here also you can combine this x and y values. Here also, just we can make use of some combination, and if you could able to draw a particular line, maybe if I'm drawing like this, is a line equation, something like this, and this particular line, okay, gives the understanding of what is the relationship, because at the end of this particular model, maybe I am inputting 15 years of experience, I should get the salary how much I can offer. Maybe 12 years of experience people, how much I offer, because I want to make use of my model so as to get the appropriate salary I can afford based on the experience. Okay, see friend, very clear na? Like years of experience is on x-axis, this is, and salary is on y-axis. Like that, there is a kind of nothing we have done. Just only we have drawn some sort of integrity here, some intersection point here, this one, and as well as this one, and there is a line drawn to this thing. And if you are observing, there are certain aspects, friends, where we are getting the first hit of this line. Okay, whatever the line we are using for the sake of understanding the years of experience and salary, okay, visually, this is what you call the intercept form. Interception. From your school mathematics, you can observe intercept, and as well as this thing is there now, guys, slope actually. Okay, so just we are getting that slope. Okay, this is what you call the slope. Now, representation wise, this thing is represented as theta naught, and this is represented as theta one. Okay, so now you may ask me, like, how come this can be asked in the certification? I am coming to that point. Now there are certain aspects which is we can name as the best fit line. Friends, be with me. So if you are referencing the best fit line, whatever the line I am drawing there, and that particular line should be best fit. How do I know that whether I am having the best fit line or not? Let me give you the equation first. You might be knowing the straight line equation, guys. Y is equal to mx plus c. Okay, and similarly, we can replicate the same equation like this according to our regression problem, beta naught, beta 1, x1. And there is technically, we are having some sort of equation like this, theta naught plus theta 1 x. Just now we have seen this is the intercept where line is originating, and this theta 1 is of course slope. Okay, so the intercept is nothing but the value of y with respect to x. Okay, the starting point according to that particular thing. So this intercept is nothing but so just I am writing value of y with respect to x, guys. Okay, why I'm focusing on this particular explanation is no matter whether you are doing the polynomial regression, multiple regression, or linear regression, in all these kind of the regression, this line equation remains same. Maybe additional parameters like beta naught, beta 1, x1, beta 2, x2, beta t, x3, like that it goes on. But the ultimate intercept and slope remains same, guys. Okay. And coming to the slope, slope indicates the steepness actually. Okay, how the appropriate line is leading, and whether it is negatively or positively leading, all these kind of the thing. Okay, and if you are referencing the appropriate best fit line, now what we need to do is okay, we observe that a kind of the relationship between the independent and dependent values, but the point is how I need to train the model actually. Okay, once we are getting into this particular thing, uh, in classification we pretty know, because the knn or all these kind of things directly yes or no kind of thing, all these aspects are remains same, how we implement and all. But in terms of regression, if I'm making use of the training the model, how we need to start to implement the modeling in case of the regression. Now there is a point, guys, here. Like suppose I'm having some sort of the equation like this, and this is the x-axis and y-axis. In the earlier case, we have taken some years of experience and salary of the corresponding persons. So what we're doing is, suppose I'm placing the appropriate values corresponding to x and y values. Maybe sometimes here, 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 like that. Now, what we are doing is we are selecting some model, and we are establishing a kind of the relationship. This is model one, maybe. And we are drawing one more model. We are establishing one more model, M2. Now, the point is, guys, here what we need to understand is, so maybe this particular M2, maybe having some predictions, and the distance is there, na? Whatever the prediction and whatever the actual value. Okay, here also there are certain predictions and certain values. Now the ultimate aim is we need to reduce the distance of the error. Okay, so whatever the prediction, whatever the actual value, if there is a minimal distance between these kind of the predictions and the actual values, then our model is good. Okay, so the distance is there, no? Whatever the value we have predicted and whatever the actual is, this is nothing but the error actually. Error, or I can say that as a residual. Error or residual. Now, error or residual is the difference between predicted value and as well as the actual value. Quite simple, no? Like error, predicted versus actual. Now, friends, remember always your predicted is yi cap and your actual is yi. Okay, just to remember, because we are going to float the appropriate metrics related to the corresponding evaluation of the model, so that you need to have that particular thing. So now, according to this particular line, okay, if I'm changing the parameters, then obviously accordingly the new lines are going to generate. Now in this particular case, error already we have seen the difference between the predicted value and as well as the actual value. So predicted value minus actual value is nothing but the error. So this is a basic equation where you can observe whether your model, if your model is having the best, I mean, if you want to quantify the best prediction, we have to minimize this error. So minimize the error between the actual and predicted is the best prediction. Okay. Up to now, simple, guys. Like regression is not much complex. So just you can make use of this line drawing, and as well as observe the line equation. How we are going to establish a kind of the relationship between dependent and independent, and training the model. But the ultimate goal is whether the appropriate model is properly, we can able to get the appropriate outcome or not in a proper way. Appropriate outcome in the sense, just you if you consider the erroneous kind of situations, like the difference between predicted value and as well as the actual. If it is more, then what it means, it is erroneous. Our model is not good. If it is less, that means whatever the predictions I am making, they are very nearest to that actual value, then we can say that is a best prediction. So obviously our aim is to minimize the error kind of thing. Now the most important topic I am starting, which they are asking plenty of questions in our certification about the cost function. Okay, because manually we cannot see how these kind of the errors can be rectified and how these things can be done. But there is a concept called cost function where I can make use of identifying the appropriate considerations. Okay, so a cost function is something like, let me define that, guys. A cost function is an important parameter. See here, okay, which is an important parameter that determines, okay, how well, how well a machine learning model, okay, performs for a given data set. See here, how a model performs for a given data set. That means, suppose if I am giving a particular data set and how your model, whether model is doing really well or if it is doing somewhat different. Okay, all these kind of things can be observed as a cost function. Okay, friends, here, no matter whether you are using the data pre-processing or machine learning algorithms or ML in Spark and deep learning, this cost function, loss function are there. Okay, in all the ways, these functions remain same, guys. Okay, first we need to understand what exactly, because these are all the metrics actually, which are pretty important. No matter how best your model is, but at the end of the day, you need to quantify your results, whether your model is really doing well or not. Those things can be decided by these functions. So what exactly this cost function does? Of course, one of the thing is related to this cost function. Basically, it calculates. Okay, just it calculates the difference between, okay, whatever the, okay, actual value and as well as the things are different between the expected value and, as I said, no, predicted value and predicted value, and which is giving as a number, as a kind of real number. I will show you. I'll talk about that, how these particular things can be estimated. And we're having many cost function trends, like the cost functions. Various methods are there. Various methods to compute the cost functions. The most frequently used, I am saying here, one is mean squared error. Okay, mean square error, which is known as the MSE. Second thing, guys, mean absolute error. Okay, MASE, mean absolute error. And our third thing is, guys, root mean square error. Root mean square error, RMSE. And another thing is there, guys, some advanced R squared, and then adjusted R square. Okay, R square and as well as the adjusted R square. Now, one by one, we'll see, guys. However, the first aspect is mean squared error. As the name implies, mean value means just we are averaging whatever the values I'm having. And however, the point here is my actual value and my implemented value square. This is what we call the mean square error, where n is nothing but this is n, guys, n, which is number of data points, maybe 1,000 or 2,000, whichever. So that refers the number of data points. And your yi, okay, observe here, guys, yi is nothing but the observed value, whereas yi cap is the predicted value, is the predicted value. Now, the MSC, which is giving that average of whatever the number of values I'm having, and error rate we are squaring, so that that becomes the mean square error. That is the first computing kind of thing where I can make use. And what is the second one, guys? Mean absolute error. So the second important thing is mean absolute error. So which is nothing but representing the average of the absolute difference between the actual and predicted values in the data set. And it measures the average of the residuals of the data set. So average of the residuals in the sense, again 1 by n remains same, and where your MAE refers sigma I equal to 1 to n. This is a common formula, and we are getting the absolute value, no? That means modulus yi minus yi cat modulus. This is the MAE. And similarly, according to that mean square error, we are having one more thing, RMSE. Don't worry about this stat, guys, because automatically our algorithm, no matter whether I'm using the MLlib of the Spark or PySpark scikit-learn, all these things basically provides some sort of the metrics and measures, but you should know that the behind the hook what's happening, because after identifying these kind of things you should be able to observe that which of the things are really giving or where I can make use of these conventions in a better way. Okay, because sometimes RMSE is better, sometimes R square is better, and sometimes adjusted R square. All those things can be observed, guys. Okay. So here, as the name implies, root mean square error, root of the MSE. Okay, so which is nothing but so whatever the specification, it measures the standard deviation actually. If you refer the variance and standard deviation, it measures. Okay, so just it is giving us the standard deviation of residuals. Now, how they are asking the question is, guys, if you want to perform the modulus kind of thing, and if I need to give the absolute values, MAE can be used. Whereas if you want to embed your standard deviation, then root mean square error. That's what the reason why we are talking about these things. We are getting such kind of the things. And next thing is, guys, R squared. Okay, this particular R squared is also known as coefficient of determination. It's quite interesting. Coefficient of determination. So which is giving that it is representing the portion of the variance in the dependent variable, which is explained by the linear regression model. So remember that, guys. If you want to represent, okay, if you want to represent proportion of the, okay, proportion of the variance. Be with me, guys, because like that they are asking in the certification. Okay, so represent proportion of the variance in the dependent variable, in the dependent variable. So which is explained by the linear models, of course. And it is what is another advantage, friends? Another advantage is scale free. Okay, it is not going to perform any kind of thing scale free. That is irrespective of the values being small or large, the value of R square always will be R square value will be always less than 1. Remember this point, guys. Sometimes, they may give identify the corresponding correctness of the R square value. Then you should be stick to your basics. R square value will always be less than 1. Okay. You may ask me this. You have given that MAE definition, RMSE definition. Now, what is R square? I'm coming to that. Just have a look on this, guys. R square. So just I'm taking this 1 minus. Okay. I'll give you this thing, guys, like sum of square residuals. Sum of square residuals by sum of square total or average. Okay. So this is sum of square residual. What do you mean by residual? Residual means error. Already we have seen. This is nothing but sum of square total or average. Okay, because we are doing that averaging of things. Okay. Now, how do I substitute the things? Y minus, what is the formula for this thing? Formula is sigma I equal to 1 to n. Okay, y, okay, so whatever the value I'm having, yi minus yi cap, actual minus predicted whole square. And there is a small distinction, guys, here. Sigma I equal to 1 to n. What we are taking here, your yi minus y bar, which is the mean value. Most important point, guys, here. How R square works is because it is comparing between this, however, mean value, mean of our y values, and this is the predicted minus actual minus predicted value. Okay, so that means your y bar specifies that mean or basic model. So sometimes guys, you need to follow this convention. Like suppose if I'm having my mean of the corresponding model, then even I can see that what is the performance. If any of the model, or if you refer the prediction, if that is less than the basic model, your model is a very bad model. Okay, so R square generally measure the performance. Now, if R square value important, if R square value less than 0, that means negative, then the model is very bad. Remember this point, guys, because R square, though it is less than 1, but it should not be negative value. If it is negative, then obviously, guys, it leads to some sort of bad representation. Compared with this, you can go with base model or mean, finding out of the mean and all these kind of the conventions. Okay, so and now last thing, which is nothing but adjusted R square. This is also pretty important model, guys, where it is taking only the appropriate. Generally, guys, if you remember in the naive base, we are having the weak learners and embedding the weak learners also. R square, what it does is just it is making use of the mean and as well as sum of square residuals, etc. But your adjusted R square, what it does is give preference to give preference to actual contributors. Okay, adjustment means what? Na? So actual contributors in the sense, suppose some features may be really adding value to our prediction. So just it is keeping track of those values and it is trying to establish a kind of the relationship between independent and as well as the dependent relationships. And definitely, as you know, is a modified version of is a modified version of R square, modified version of R square. And then and if it is adjusted for the number of independent variables in the model, and it will be always less than or equal to R square. So that means your adjusted R square less than or equal to R square. That is the idea, of course. Now, what is the formula for that? So just you observe here, adjusted R square is equal to 1 minus. Okay, so just we are making use of don't worry, guys, 1 minus R square, number of values, minus 1 by n minus p minus 1. Okay, so this n is nothing but number of data points. N is the number of data points. And your one more thing is p is nothing but number of independent features. Independent is, however, one number of independent features for x values. So based on that kind of the convention, you can find out the R square. So far what we have seen, guys, mean square error, mean absolute error, root mean square error, R square, adjusted R square. Okay, the questions already I have given, like in root mean square error, just standard deviation kind of the calculation. And to scale internally, just we need to use the R square, always value less than 1. And if R square value less than or negative, then that is a bad model. Adjusted R square, which is giving preference to the real contributors. And of course, adjusted R square is nearest to the R square value. That thing we have observed. And your mean square error and mean absolute error, two common things like mean square error, yi minus yi cap whole square, and of course, just we are taking use of this averaging. And absolute error, just we are taking only modulus operator. And one of the advantage with R square is just we are making use of that mean also. If you refer the point here, okay, mean value also we are scoping. So as to estimate whether how our model is really performing. So just one simple question I'm asking guys, which we got in certification actually. The question is like this: which of the following metrics, which of the following metrics is not suitable to evaluate in machine learning, AutoML or ML experiments through regression? Through regression. Friends, you need to observe not suitable. Especially in Databricks, guys, they ask this incorrect statement, not suitable, many times. In that case, you have to identify the not suitable one. That becomes the correct answer. Okay. Now the options are: your A option is F1, B option is R squared, your C option is RMSE, and option D is MAE. Of course, five options would be there no, in our exam. So mean square error. Okay. So you need to eliminate the metrics which are not belonging to the regression. Let us try to understand the question first. Which of the following metrics is not suitable to evaluate an ML experiment through regression? Just now we have seen regression is a algorithm belongs to supervised kind of the learning, and this regression is used to establish a kind of the relationship between the dependent and as well as the independent variable. That is the basis for the regression kind of thing. And next important thing is where if you are making use of this regression, there are certain metrics. As we discussed, we are seeing that MSE, MAE, RMSE, R square, just now we have seen. But we have not observed this F1 actually. I'll talk about this guys, but answer is this answer, okay, F1 not for regression. So this answer is correct because the question is like this: out of the following metrics, which metrics is not suitable for the regression? F1 is not for the regression because your R square, which is a regressive measure, regression metric, and RMSE, MAE, and MSE, all these things are measures of regression. Okay, so like that, but just you should know that how we are making use of the convention of observing the regressions and all these kind of the conventions. Now let me introduce the other matrix test because as I said, no, in both the regression and as well as the classification kind of thing, we are getting the questions. Uh, there in classification, guys, generally in classification, there is a concept called performance matrix. Okay, performance matrix. This is also quite interesting. In this, we are having certain metrics actually for the classification. How in the regression we are having MSE, mean square error, mean absolute error, root mean square error, R square, adjusted R square, like that. We are having classification measures also. Most frequently used kind of thing is the confusion matrix. Already we have discussed this thing. And second thing is the accuracy. We are getting questions from this also. Next is the precision. precision, then is the recall, precision recall, and then F1. Now we have seen F score or F1 score. Just this wrong answer is there. No? Actually, not suitable. But this is the classification measure actually. Friends. F1 is the classification measure. Now let us discuss one by one because once we see the measures of the regression, there is a chance of observing the measures of the classification also. For that, we're having these things actually. Like performance metrics wise, confusion matrix, accuracy, precision, recall, and F measure or F score. The most frequently used thing is because though we discussed the confusion matrix earlier, but without mentioning the terminology of the confusion matrix, we cannot hold this accuracy, precision, recall, all these kind of things. So let me introduce that first aspect. Okay, how this confusion matrix helps us. Okay, this confusion matrix is that something like that compares the number of predictions for each class that are correct and those that are incorrect. The advantage of this thing, guys, actually this gives the correct answers and as well as the incorrect answers also. Suppose to explain this thing, I'm having the true positive here and false positive, and we're having false negatives and true negative. Now, generally, guys, these two measures should be less. Okay, if false positive and false negative are less, then our model is successful. Now, to notify this side, we are making use the actual values. Okay, 1 0 kind of thing, yes or no, because classification binary, and this is predicted all your predicted values. Now, this let me give you this convention: true positive, and then false positive, uh, true negative, and false negative. So, true positive, positive value, the number of positive observations, the model predicted as positive. So, positive observations predicted as positive. Simply, I'm giving guys. Observations are positive. Your model also predicted as positive. And the number of negative observations, okay, the model incorrectly predicted as positive. Okay, predicted as positive. Actually, they are negative, but your model predicted as a positive kind of thing. True negative, the number of negative observations. Oh, running low. 1 minute, guys. Number of observations, negative observations, true negative kind of thing. The model correctly predicted as negative, actual negative, and they also predicted as negative. And your false a negative number of positive observations, the model incorrectly predicted as negative. Okay, so a probability, like plus minus, if I'm having how many times plus properly identified as plus, and how many times minus identified as properly. Okay, now so at the outset, actually positive and positive, true positive is correct prediction actually in terms of prediction if I'm writing. Okay, positive and positive. And next important thing is false positive. Okay, so which is the appropriate incorrect, because actually our observation is negative, but your this prediction is positive, which is incorrect. Whereas if I'm talking about the false negative, this is also incorrect because our observations are positive, but our prediction is negative, false negative. Then true negative, which is again correct. Okay. So at the moment you talk about this true positive, false negative, true negative, all these things should come into your mind. Now, let me introduce one more thing, guys, and then we'll wind up. So the accuracy and as well as precision, these two things I'll compute. Quite interesting, it actually. We know confusion matrix without any confusion, but accuracy and precision definitely leads some kind of the confusion. But let me define that. What do you mean by the accuracy? Accuracy is defined as the rate of correct predictions. Okay, that means the ratio of correct predictions. Okay, ratio of correct predictions to the to total number of predictions or observations. That means I'm having some certain total predictions. Okay, this is the total predictions, and how many of them are correct? Maybe thousand I'm having, and how many correct predictions are made? That is what you call the accuracy. Accuracy. Now, in terms of your confusion matrix, guys, just I'm making use of the correct predictions. True positive is correct, false negative is correct. Okay, correct predictions actually false negative, and then we are taking that true positive, uh, false positive, false negative, and true negative, because total means everything. Correct predictions are true positive and false negative. Now let me give you this example of the confusion matrix. 5, 2, and then we're having 1 and 2. Okay, guys. Okay, now how do I take this particular thing? Actually, we have seen this these things. You know, this should be less actually. Okay, this should be more. Now, let me substitute this kind in the accuracy. Accuracy is equal to, so first thing is true positive. Value is 5 plus false negative. Okay, our value is 2. So just we are making use of the false negative 2. And then by total values, true positive and true negative. So just I am making use of that false positive and false negative. The total 7 by 10. So 70 percentage of the appropriate model is correct. I mean, suppose if I'm taking 10 cases, out of 10, 7 correct measures are there. And if you compute manually also, 5 plus 2, 7. Out of 10, 7 times we got the correct answers. So obviously your model is 70% accurate. Not bad, but 70% is normal, guys. It's not a good thing actually. But most importantly, in the decisions, there is another thing called precision actually. Okay. Uh, See, one thing, guys, here, why compared with accuracy, precision is taken by the most of the data scientists is precision is defined both for pass or fail, because in the accuracy, I am focusing on the correctness. So that means precision of pass divided by precision of fail. So that means this thing definitely gives the understanding of correctness and incorrectness also. Now your precision formula is like this. Okay, how do I compute this thing is correctly predicted pass or fail. Either of things I can embed, and actual pass or fail. That means one simple analogy in the earlier accuracy, I am taking entire things, total predictions. Out of that, how many are correct? But in this precision, suppose the number of pass is there. How many times our model identified them as pass? If number of fails are there, how many times our model predicted them as fail? Okay, so now if I am taking like this precision of pass, okay, which is nothing but formula, guys, true positive by, okay, true positive plus false positive. Okay, true positive plus false positive. Here we have taken some example, na? 5 to 1 2 kind of thing. Now let me compute that true positive values. 5 by 5 plus 2. Out of 7, five times we could able to get the correct answers. I mean, out of seven true, five truths. Okay, and coming to the precision of fail. Okay, separately I can compute. What is the formula for that? True negative by true negative plus false negative. If you see from this confusion matrix, true negative and all these values I got. So your true negative values 2 by 2 plus 1. Out of three cases, two times we could able to correctly identify the failure cases. So 2 by 3. So the main aim of this particular precision, guys, to reduce the wrong predictions. Okay, so precision main aim is to reduce the wrong prediction. This is the perfect measure, guys, actually, compared with the accuracy, because accuracy is always talking about your correctness. 1 minute, guys. Okay, I'll complete because this